This week, our content will be about synthesis basics. This week's content will focus on defining the essential elements of synthesis and synthesis theory, understanding terminology associated with the three modules of the synthesis model and how they are used to create sounds, and we will discuss the many parameters and settings associated with synthesis and its modules. No matter if the synthesizer is software or hardware, old or new, it relies upon a basic synthesis model that consists of three main parts: oscillator, filter, and amplifier. Understanding these three basic parts is the first step towards successfully using a synthesizer. Since we are working with software instruments in a digital audio workstation, we now need to know how to control the sounds they create. Software instrument plugins are a type of synthesizer. We sometimes call them software synthesizers. The broad term for synthesizer is an electrical or electronic musical instrument that produces sounds by generating and combining signals of different frequencies and amplitudes. Synthesis is the process of creating sounds from scratch using electronic signals and instruments to create sound waves. Regardless of whether the synthesizer is a physical or virtual one, whether it has a keyboard, whether it has pads or sliders, or just simply antennae like a theremin, we can think of the generation of sound as a process that involves three basic modules: the oscillator, which generates an electronic sound; the filter, which modifies the timbre of the signal; and the amplifier, which articulates the sound and provides the overall amplitude level. These three modules are generally found in this order in any synthesizer signal path. We will discuss how each of these modules are useful to the art of sound design. Note that the picture on the right shows these three modules in their order with their designated shapes. We use flowcharts sometimes to show how sounds are designed and the modules that are at work in each sound. Oscillators are typically circles, filters are typically squares, and amplifiers are typically triangles pointing to the right. Oscillators is where the sound begins. The oscillator generates an electric signal for the purpose of synthesizing audio. This is where the signal path begins in any synthesizer. Most synthesizers have a group of oscillators or an oscillator bank that allows the user to build a sound spectrum by mixing together oscillator output. We can see in the picture on the right the photo of the oscillator bank for the Mini Moog, which is a very, very awesome vintage synthesizer which was used in many recordings from the 1970s and onward. This oscillator bank consists of three oscillators labeled as such: oscillator 1, oscillator 2, and oscillator 3. When we press a key on this synthesizer, we can choose how much of each oscillator is in the signal. Oscillators often have the following parameters. Tuning or frequency selects the initial frequency of the oscillator. Typically, oscillators produce a signal between 20 and 20,000 hertz because that is the human hearing range. However, we can tune an oscillator to theoretically any frequency, and you'll notice that in this oscillator bank from our Mini Moog that this center dial allows us to change the tuning of this oscillator either upwards or downwards. Often this is helpful for creating maybe an array of intervals or something other than octaves. We can also change the octave per se with this left-hand knob here too. So these are referencing organ pipes of 16 foot, 8 foot, 4 foot, and 2 foot. And this comes from a tradition of organ playing and pulling out different stops to create overtones. So a 16 foot is is twice as low as the 8 foot, which is twice as low as the 4 foot, and so on and so forth. These selections allow oscillator 2 to always be 2 octaves above oscillator 1, for instance, and oscillator 3 to be 1 octave above this one or this one. The wave shape selector selects the initial spectrum of the audio signal. We see that knob on the right. This waveform selector allows us to choose between triangle, sawtooth, square waves, and the like. The range selects the relative octave, which I just discussed. Since the purpose of the oscillator is to begin the process of generating tone and initial timbre, as we saw in the previous slide, we can select the timbral properties of the beginning signal. The wave shape function allows the user to select the initial waveform algorithm, which in turn determines the initial timbre and overtone spectrum. On the right, we have pictures of the 4 basic wave shapes and the overtones that they generate. So the sine tone generates only a fundamental. It is the most pure tone of the 4. The second one is the triangle wave, which is a fundamental and alternating overtones, but very quiet. It sounds a lot like a sine wave, but it's slightly more bright. The third wave is the square wave, which is fundamental plus more overtones, more volume from the same overtones as the triangle wave. It sounds even brighter. And then finally, the sawtooth wave gives you the fundamental plus all the possible overtones, which is the brightest of all. When starting a process of synthesizing a sound, we can choose the beginning timbre to be pure or extremely bright, depending on what kind of sound we want to generate. The purpose of an oscillator bank is to build a sound spectrum by combining the output of an array of oscillators. The technique associated with this is called additive synthesis. Additive synthesis is a synthesis technique that relies on the combination of waveforms at different amplitudes. Similar to the technique of using multiple organ stops to play 2 or 3 octaves at once on an organ, synthesizers often combine multiple waveforms and at different octaves to create interesting timbres and textures. The flowchart on the right shows us how we can conceptualize with a schematic 3 oscillators being controlled by 1 press of a keyboard. If we press a note on our keyboard controller, theoretically that could go and trigger 3 different oscillators tuned in various ways, each oscillator selecting its own waveform. This one could be a sawtooth wave, this one could be a square wave, this one could be a triangle wave. All of them could be placed at different octaves, so that when we play different notes on our keyboard controller, that same spectrum is continued throughout the entire keyboard range. The mixer also allows us to change the levels of each of these oscillators. We can select more sawtooth wave, for instance, or more triangle wave to dial in, again, the timbre of the initial sound. It then goes to the VCA, or the amplifier, which we will discuss later, to control how it is articulated. Oscillators typically produce a waveform within the human hearing range, which is 20 to 20,000 Hertz. However, low-frequency oscillators, called LFOs, produce a frequency below 20 Hertz. When they do, they create a waveform that a human doesn't hear as pitch. However, when the frequency is that slow, it can be detected as rhythm. It can only be detected as rhythm if it is applied to different parts of the synthesizer path, to create rhythmic changes in volume and pitch. This is a very common technique called modulation. Modulation is the rhythmic changing of a sound parameter over time, such as the frequency, amplitude, or filter cutoff frequency of a sound. This rhythmic change results in the sensation of tremolo or vibrato, depending on which parameter of the signal path is being modulated. Remember that low frequency oscillators are also regular oscillators in that you can select a wave shape, right? And you can select its initial frequency below 20 hertz. So the faster the speed is related to the higher hertz number. So a very low hertz number will produce a very slow change. LFOs are found on almost every synthesizer, and often they are mapped to the modulation wheel on the left side of its controller. The next module is called the filter. Filters, as we know, modify the timbre of any sound. Most filters rely on a common parameter called the cutoff frequency. A cutoff frequency is a chosen frequency at which a filter begins to reduce energy and thereby change the timbre. Here's a list of the most common filter types. They are pictured on the right. The high-pass filter allows high frequencies to pass through above a chosen cutoff frequency. A low-pass filter allows low frequencies to pass below a chosen cutoff frequency. Band pass and band reject filters allow a select group of frequencies to either pass or be rejected around a center frequency, thereby creating a channel by which to pass or reject frequencies. Sometimes the band reject filter is called a notch filter. Sometimes the band pass filter is called a peak filter because of the shapes that they create in the audio spectrum. When using modulation, we often modulate the cutoff frequency of a filter. Changing the cutoff frequency of any of these filters results in a filter sweep, which is a very common technique. Finally, the amplifier is the last and third module. The amplifier not only controls the overall level of the sound, but it also controls the amplitude envelope. The amplitude envelope controls the articulation of the sound, or how the sound will begin and end once it is triggered by the keyboard. This is an extremely important part of sound design. The amplitude envelope is the characteristics of the sound that provide its personality, from staccato to legato to smooth to percussive to bowed to bell tones. All of these different sounds have different amplitude envelopes that are customizable in any synthesizer. All of these times and levels correspond to the pressing of a key on the keyboard controller portion of the synthesizer. The attack time is the amount of time from silence to full volume when triggered. We can picture the pressing of a key at this vertical point in time on the left. If we press the key, if the attack time is slow, the sound will gradually bloom. If the attack time is very short, then the sound will begin immediately. Decay time is the amount of time of initial decay after pressing the key. Pianos, for example, have a decay after their initial press. The sustain level of a sound, if any, is the level of amplitude while the key is held down. If you've ever played on different presets of a synthesizer, you'll know that some of the sounds, when you hold down the key, do not continue to make a sound. A good example is the difference between a piano and a mallet sound versus an organ or a synthesizer sound. An organ sound, if you hold down the key, the sound will continue to sustain. This level of sustain can be controlled with this value. Finally, the release time of the sound is the amount of time from sound to silence after the key is released or lifted. If I hold down a key for sustain and then release the key, that begins this timeline from this point to the end, giving us a sense of decay or release. These 4 parameters are often abbreviated ADSR for attack, decay, sustain, and release. We can find these parameters present in almost any synthesizer. All synthesizers, hardware or software, new or old, have a variety of parameters, all of which can be categorized into one of these 3 main parts: oscillator, filter, or amplifier. Knowing the basic roles that they play allows us to have an idea about what they do to the sound. All modern synthesizers, hardware or software, also have a bank of presets, or a list of pre-programmed possible sounds that come from the manufacturer. Presets can be very, very helpful and useful, no matter your level of experience. A user of any level can explore the presets of any synthesizer to get to know what it can do. It lets you know the breadth and the spectrum of sounds that are possible in this synth. It can also provide a starting point for dialing in the sound that you can hear in your mind, that you may not know how to build from scratch. A user can typically also modify a preset and save it in a user bank and to create a list of their own sounds for future use.